Stoichiometry of chemical reactions. So performing stoichiometric calculations requires the following information. You need to know what kind of reaction you're doing, and it's going to depend on the nature of the chemicals when they are dissolved. These things are going to behave differently in aqueous solution than they are going to as a solid. The amounts of chemicals present in the solution we're going to express as concentrations. Right, we got a couple of different units for concentrations. Right, we can spend a whole section on different types of concentration units, but the one we're going to use most commonly, and the one I want you to really know and become familiar with, is one called molarity. So molarity is given the symbol uppercase M, right, and it's moles of solute per liters of solution. So a solution that is 1 molar, right, and we can call it 1.0 M, contains 1 mole of solution, solute per liter of solution. Right? Sometimes you will also see this written out as square brackets. Right? So if I talk about my concentration of Na plus ions, that is the same thing as saying moles of Na plus per liter of Na plus solution, which is the same thing as saying capital M. Right? So 3 different ways to express the same thing. Right, so let's calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution. Right, so what we're going to do, right, we'll plan our little roadmap here. We're going to go from grams of NaOH, and then we're going to take that into moles of NaOH, and then we're going to go into molarity. Right, so here we're going to use our molecular mass. Here we're going to divide by the volume in liters, and then we'll end up with moles per liter. That's our unit of molarity. So that's our plan. Okay? So our objective, find the number of moles of sodium hydroxide. We've been told we've got 11.5 grams of sodium hydroxide and 1.5 liters of solution. What we need is moles of solute to calculate the molarity in terms of moles of solute per liter of solution. Right, so the first thing we do is we convert this 11.5 grams of sodium hydroxide. When we divide by the molar mass, 1 mole of sodium hydroxide per 40 grams of sodium hydroxide gives us 0.288 moles of sodium hydroxide. Then to compute the molarity, that's moles of solute per liter of solution. Well, we just had moles right there. Right? And we were told in the preceding slide that it was 1.5 liters of solution. All we do is divide, and we end up with 0.192 moles per liter of sodium hydroxide, or 1.92 molar sodium hydroxide. Right, we can also do 0.192 molar. Right, how do you figure out how many moles of something that do you have in a solute? So you take a sample, and the number of moles present in the sample are going to be determined. The molarity of the solution is multiplied by the volume of the sample. So you're going to do volume times concentration is equal to moles, right? All that is doing is taking the equation that says moles per liter, my molarity, my concentration is equal to moles over volume. Right? So our volume is going to be in liters, our concentration is going to be in moles per liter, and our moles are going to be in moles. Right? So all I'm doing is rearranging that equation. Right, so calculate the number of moles of chloride ions in 1.75 liters of 1 times 10 to the minus 3 molar zinc chloride. Right? So looking at this guy, right, I've got a volume, and I've got a concentration. But I want to be careful because I want the chloride ions, and this guy has a 2 in here. So when I take this and I dissolve it in concentration, right, my concentration of zinc is going to be equal to, right, I'm going to have twice as many chlorines, right? So I'm going to have twice as many chlorines. So for every zinc, right, it's got zinc chloride, that's going to dissolve into zinc 2 plus and 2 Cl minuses. So watch this molecular formula so you don't get caught out by the number of things. Make sure you look at what you are trying to solve for. Find the moles of chloride ion in solution. We're told that we've got a concentration of zinc chloride and we've got a volume. If I've got a volume and a concentration, I've got moles. Right? We're going to need a balanced chemical equation for dissolving the zinc chloride. So for our balanced chemical equation, it's going to be zinc chloride in water is going to give us zinc 2 plus and 2 Cl minuses. Then we need to calculate the molarity of the chloride. So we're going to take the concentration of our zinc chloride and multiply it by 2, because for every 1 mole of zinc chloride, we're going to have 2 moles of Cl minus. All right, so we've got 2 times 10 to the minus 3 molar chloride. Once we know the concentration of Cl minus, that's when we're going to do our volume times our concentration. So we'll take our 1.75 liters of solution times 2.0 times 10 to the minus 3 moles per liter. Right? Our liters will cancel out. And we end up with 3.5 times 10 to the minus third moles of chlorine ions in that 1.75 liters of solution. Right? So changing the volume does not inherently change the concentration, because if you are decreasing your sample size, like say we took a little eyedropper, right? A little eyedropper here, right? And we've got this a little drop, right? Like 1 milliliter. Well, I've reduced the volume, right? I've got 0.001 liters, but in that 0.001 liters, I've got far fewer moles. Right? It's the ratio of moles per unit volume that gives us the concentration, and the concentration does not change based on our sample size. Right? You scale up the sample size, you increase the number of moles. You decrease the number of moles, you got to decrease the volume along with it. Right? Now, dilution is something a little bit different. That's when you add water to a concentrated solution in order to achieve a desired or target molarity. The pieces of apparatus used in the process of dilution are going to be either volumetric pipettes, which come in specific sizes, 5, 10, 25. These guys are going to be more accurate. Right? Or they're going to be measuring pipettes. So these guys are going to be variable volume. But they're going to have less precision. And this is our volumetric, and this is a measuring pipette. Those are all sometimes called Moore pipettes. So we can ask questions like, what volume of 16 molar sulfuric acid must be used to prepare a 1.5 liters of 0.1 molar solution? So looking at the things we've got, right, we are trying to find out what volume do we need if we're given an initial concentration and 2 final concentrations. So how much of this concentrated stuff, right, do I need to make a given target volume and concentration? How much do I need to put in here, right, to make that work out? All right, we know the volume, 1.5 liters, and we know the concentration, 0.1 molar. Right? If I take these two things together, what do I have? Right? I've got moles. What we're going to do is we're going to do the same thing on the other side, except here, right, we know what the moles are from this dude. Right? We know what the concentration is. We're going to try to find this. So we can do it this way. You can set up, find the moles. The moles on the left equal the moles on the right. We know the concentration here. We're going to try and find this. So that's another way to do what we're going to do up here in a second, right? So to find the volume of the H2SO4 required to prepare the solution, we've got our target volume, right? We've got our target concentration, and we've got our initial concentration. So we need to figure out how many moles are required in the solution. So the first thing we do is we're going to figure out number of moles using volume times concentration. So V times C or M times C, it's going to give us moles. 1.5 liters of solution. We had 0.1 moles of H2SO4 per liter, right? That's our concentration. Right? Our liters cancel out. It gives us 0.15 moles of H2SO4. To determine the volume of 16 molar H2SO4 that contains this many moles, we're just going to rearrange that equation. So we're going to do volume times 16 moles of H2SO4 per liter is equal to 0.15 moles. And now we're just going to solve for V. Okay. I'm going to rearrange it. All right, we're going to do 0.15 moles of H2SO4 divided by 16 moles of H2SO4 per liter. And we're going to end up with 9.4 times 10 to the minus 3 liters, or 9.4 milliliters of solution. So to make our 1.5 liters of 0.1 molar H2SO4 using 16 molar H2SO4, we're going to use 9.4 milliliters that we're going to add to this 1.5 liters of water. Now, when we do this, right, here is an important point. You're going to do it like this, right? You're going to put in your 9 milliliters, right, 9 milliliters, and then you're going to add in volume so that the total volume is going to be equal to 1.5 liters. You are not going to start with 1.5 liters and then add in your 9.4 milliliters. Don't do it that way, right? That's going to lead you to an erroneously low solution concentration, because here with this guy, your volume is going to be equal to 1,500 milliliters plus 9.4, so you'd have 1.5094 liters, and that is not the same thing as 1.5 liters. So your concentration is going to be low. So you add the stuff in and then you dilute to the line or you fill it up, but your total volume has to be 1.5. An alternate way to express this concept is by the following equation. It says M1V1 equals M2V2. And really all that is saying, if I've got a volume and a concentration, is that moles are going to be equal to moles. And you can ask, right, I've got 4 variables, I can ask 4 questions. Whatever you're going to do, right, it's going to end up being expressed as a ratio of 2 things times another. So M1 and V1 are the molarity and the volume of the solution before. M2 and V2 are the molarity and volume of the solution afterwards. If I'm doing like the equation we just saw, right, I want to know what volume of our concentrated stuff. Well, that's going to be equal to M2 V2 over M1. Right? Well, if I rearrange that, it's saying my new volume is going to be my target volume, or my final volume, times the ratio of my masses, or my concentrations. Right? And if I was looking for a concentration, right, it would be whatever my concentration is times a ratio of the volumes. Right, so you can think about this ratiometrically. Right, so I'm doing a 2-to-1 dilution, right? Making it go from 2 molar to 1 molar, or 1 molar to half a molar. How much do I need to dilute it by? Right? That's one way. That's another way to think about this. All right, let's do a real quick concept check. Which of the following solution contains the greatest number of ions? All right, so you got 400 milliliters of 0.1 molar sodium chloride, 300 milliliters of 0.1 molar calcium chloride, 200 milliliters of 0.1 molar iron chloride, or 800 milliliters of 0.1 molar sucrose. All right, let's pause. Think about it. Okay, let's analyze. The sucrose is going to be right out, right, because it's not going to form any ions whatsoever. Now, looking at the rest of them, can we see anything that's going to be obvious? Well, we've got different volumes and we've got different numbers of things. This is going to dissolve into Na plus and Cl minus. This calcium chloride will dissolve into calcium 2 plus and 2 Cl minuses. And this iron chloride will dissolve into iron 3 plus and 3 Cl minuses. So when we take this iron chloride, we need to take whatever this number of moles is and multiply it, if we're looking at the ions, by 4, right? Because I've got 1, 2, 3, 4 things. And this calcium chloride, I need to take this 0.1 molar and I need to multiply it by 3, because I'm going to end up with 3 ions in solution. And this sodium chloride, I need to multiply by 2. So we're going to change this to ions. Right? I'm going to have 0.2 moles per liter of ions of my sodium chloride. And I'll have 0.3 moles per liter of ions for my calcium chloride. And I'll have 0.4 moles per liter of my iron chloride ions. Right? Then we look at the volume and see which one is. So for the sodium chloride, it'd be 0.4 liters times 0.2 moles per liter, and that's going to give us 0.08 moles of ions. If we do the calcium chloride, we're going to have 0.3 liters, and then we'll multiply that by 0.3 moles of ions per liter, and that's going to be 0.09 moles of ions. And for our iron trichloride here, our iron 3 chloride, we would have 0.2 liters times 0.4 moles per liter, and that's going to give us 0.08. So the one with the most is going to be this calcium chloride. Another quick concept check. A half-molar solution of sodium chloride in an open beaker sits on a lab bench. Which of the following would decrease the concentration of the salt solution? Adding water to the solution, pouring some of the solution down the sink drain, adding more sodium chloride to the solution, or D, letting the solution sit out in the open air for a couple of days. All right, pause. Come back. Okay, let's take a look. So we're looking at what's going to decrease the concentration of the solution. Right? If our concentration is in moles per liter and we want to drop that, I've got two things I can do. I can decrease moles, or I can increase the volume. So if I add water to the solution, I've not changed the number of moles, but I have increased the volume, therefore my concentration goes down. Right? So A would work. If I take some of my solution and I pour it down the drain, what's happened? Well, I've decreased the volume, but I've also poured out some of my moles. So I've decreased my moles also, and I have not changed the concentration. Right? If I add more sodium chloride to the solution, I've increased my moles. Right? No change in the volume, therefore I'm increasing my concentration. If I let the solution sit out in the open air for a couple of days, my volume is going to go down, but my moles remain the same, so my concentration, I've got more moles in a smaller volume, my concentration goes up. Okay? So let's take a quick look at a couple of different reaction types.